promised Ventali that this would take only 20 minutes.
This meeting is being recorded.
I'm fine with this meeting being recorded. The setting is in in zero knowledge or succinctly verifiable proof systems, and most of the moon math goes into the proof system itself, but we are actually concerned with what goes on in the computation. Typically, you want to evaluate a hash function. Hash function is obviously the basis of a lot of cryptography. And since we're applying this in a zero-knowledge or succinctly verifiable proof system, we want the hash function to be efficient for that use case. And simultaneously with Rescue, or more or less simultaneously, other authors published Poseidon. That has seen a lot of adoption, and since there have been other proposals such as reinforced concrete and a few others even. This presentation summarizes Rescue Prime, which is an update to Rescue. And in terms of performance, Rescue is the prime field hash function that performs best when counting the number of constraints either in R1CS format or the size of the execution trace in a Stark context. It performs best only by a hair, outperforming Poseidon, whose main selling point is that it performs a lot better on the CPU. So if you want a faster hash function, maybe Poseidon is the way to go. If you want to minimize the number of constraints, maybe Rescue is the way to go. So this was the original paper. This is known as the Marvelous paper, and it is written for other academics and to please other academics, but it's not really very comprehensible for implementers. And so that's why we wrote the update, Rescue Prime, which covers only Rescue Prime. And this paper, we actually tried to publish it, but all the reviewers rejected it because there is no scientific novelty, and we are quite explicit about providing no scientific novelty. So the contributions are, we have an easy to follow specification, and we call it a standard specification. So now we have a standard also, and it's simplified. So I guess we did change a few things. Now it's simpler, but it's really just a specification. So if you follow the paper, you should end up with the same hash function that other people implement if they follow the same paper. So what's the difference? We flip the order of the S boxes with respect to Rescue. We simplify the derivation of round constants, and we reduce the security margin. So the construction, I guess, is not that important. This is how you go from a Rescue block cipher all the way to a hash function, and you apply various transformations, each of which has a security proof in the literature. In the Rescue Prime paper, we cover two stages of this pipeline. Rescue XLEX is the permutation, and Rescue Prime is the hash function. Other authors like to call it 49, but I think XLEX is the right pronunciation. So this was Rescue Prime. This is Rescue Prime, and we are changing the round constants, and we are also flipping the order of the S boxes. So in Rescue, the alpha inverse came first, and now in Rescue Prime, the alpha comes first, followed by the alpha inverse. And the reason why it's okay to do this is because we can always append a half round to either side of the function. So we have the same internal stuff, and we just add in total one extra round, and that's not going to hamper security. But we do have to take into account that there's an n+1 now where there used to be an n. In exchange for starting with the regular alpha and doing the alpha inverse second, we get to fold across the entire cipher when we arithmetize it, and that gives rise to a simpler arithmetization. The truncated sponge is essentially saying that you can absorb in any number of iterations, but there's only one iteration where you can squeeze out. Now we see some considerations about security. So the bottleneck attack, which will end up being the attack that you need to take into account to set parameters, is a Grosvenor basis solver. So in a Grosvenor basis algorithm, the input is a list of polynomials in many variables, and the output is supposed to be a solution to those polynomials. Or I guess the Grosvenor basis is, technically speaking, another list of polynomials that is equivalent in some sense, but the whole point of sending one system of polynomials to another system of polynomials is that the output is easier to work with. For instance, it allows reading out a solution. And so the way it does is you build a huge matrix called the Macaulay matrix, in which every row represents the coefficients of one of the polynomials, and every column represents a monomial. And then you just populate that with the system of polynomials that you start with. And then you apply linear algebra, but your matrix is wider than it is tall. So linear algebra won't get you very far. So what you do then is you start multiplying these polynomials by other polynomials, and that's how you get non-zero coefficients in the columns on the left. After multiplying this enough, you can populate this entire matrix, and if you're lucky, you can apply Gauss and extract a Grosvenor basis, or in fact, you can extract the solution directly. So the question is, how expensive is it to run Gaussian elimination on this huge matrix? And to answer that, we need to know how big is this matrix going to be. And it depends on a parameter called D, which is the degree of regularity. And roughly speaking, it corresponds to how difficult is it to find a solution to this system of polynomials. So from a designer of hash functions point of view, you want D to be as large as possible. Small d is bad from a designer's point of view. From the attacker's point of view, it's obviously the other way around. Here is the formal definition of the degree of regularity. It kind of captures the worst case behavior, and it's conjectured that random systems of polynomials behave regularly with overwhelming probability. There is a nice formal power series representation or expansion for it. It really doesn't matter, because in the regime we are interested in, the numerator and the denominator cancel, and we have a simple expression, which is the Macaulay bound. And based on expressions, we find that the concrete observed degree of regularity for rescue is actually less than what we would expect based on this bound. So there is some degradation there. Having said that, the observed concrete degree of regularity does fit on a line, or at least from a few the few data points that we were able to collect. And so based on this consideration, we decided whatever security estimate we get from extrapolating the orange line, we add a significant margin to guarantee that the Grosvenor attack is sufficiently difficult to perform. So concretely, the number of columns in your matrix is degree of regularity plus number of variables, choose number of variables, raised to the power of omega, where omega is the linear algebra constant. That's 3 for Gauss's algorithm. 2 is a lower bound, and I think the current best algorithm is 2.37 something. And that gives you a plot of the evolution of security as a function of the number of rounds. So this is the plot of the evolution of the attack complexity in a Grosvenor basis attack. And so rescue had a larger security margin, rescue prime has a smaller security margin, but we are still on the safe side with that margin. That brings us to a conclusion, and I guess the conclusion is that rescue prime is a new and updated version of rescue. So those were the slides, and I also have one more note I'd like to visit, got it. Which is the new report that we were commissioned to make. Hang on. I need to share screen again. I am screen sharing, but that stops sharing and then share again. Select window or screen, entire screen. Here we go. So in recent weeks, we concluded a research project where we decided to optimize rescue prime, tailored to a specific field and use case context. The use case was a start virtual machine, and the field is the field with 2 to the 64 minus 2 to the 32 plus 1 elements, erroneously called by some people the Goldilocks field. I say erroneously because the Goldilocks field obviously denotes another prime. So what's going on in this report? Well, the conclusion is that the only thing we can really do to make it faster is to shift to a circulant MBS matrix. And so we supply one here for the state size of 12 elements, and we supply one here for state size of 16 elements. And beyond that, there's not a whole lot you can do to make it faster, by which I should be clear what I mean. There's a lot you can do to make it faster, but every one of those possible techniques introduces more questions in terms of security. Now, this report also does a few more things, but all of these few other things, they're just optimizing the easy to use rescue from the VM's perspective, not how to make it faster on a CPU. So this report is already public and shareable, so how about I just drop it in the chat here, and then we can move on to a discussion.
Thank you for the presentation. That was really interesting. You touched on the Grosvenor basis attacks, which seem to be like sort of the say main attack against these sorts of snark-friendly hash functions. And I'm curious, just because, as I understand it, the goal of Rescue and Poseidon and some of these is to be like simple and short to represent in arithmetic circuits. Shouldn't that give you like a canonical polynomial representation? Is it like I'm just thinking again like about the trade-offs between, you know, circuit size, efficiency, security. Yeah.
Yeah. For univariate polynomials, it's easy to find a canonical representation. You just order your terms by descending degree, and then you have a canonical representation. For multivariate polynomials, it's kind of difficult, because even if you introduce an ordering of terms, you could still have two lists of polynomials that are correctly ordered, or hang on, two lists of polynomials whose terms are correctly ordered, and even the polynomials are correctly ordered within those two lists. You could still have two such lists, and they have exactly the same solution set, and they are different, and they're just enforcing the correct ordering of the terms does not give you a unique way to represent the set of the ideal of polynomials. So an ideal is the generalization of a subspace. You take any linear combination of your polynomials where the coefficient of this linear combination can themselves be polynomials. Then you have the ideal. And the only way we know of to test for ideal equality, which is what you're looking for if you want to have a canonical representation, is to compute the Grosvenor basis. Phrased differently, Grosvenor bases are the tool with which you get a canonical representation.
So we're essentially looking for a kind of like a ubiquitous algebraic variety. Is that one way of putting it?
I'm not sure what you mean by ubiquitous.
Well, in that the ideal defining it is canonical in some way, which you don't get in the multivariate case.
I guess, but then even if you study Grosvenor basis algorithms, you'll observe that you can choose any monomial ordering and you can define a Grosvenor basis with respect to any monomial ordering. And then you end up with a different Grosvenor basis with respect to different monomial orderings. So you have to choose a monomial ordering, and then you get the Grosvenor basis relative to that ordering. Yeah, I'm happy to answer questions about Grosvenor basis, about rescue prime. I'm also happy to attempt to answer questions about Poseidon or reinforced concrete, but I'm not an expert there, and so I would risk getting things wrong.
Alan, I was wondering, I think in the rescue paper, the original paper, it mentions that the performance, well, basically because of the larger safety margins compared to Poseidon, it has a strong effect on the performance. So with the updated, with the lowered safety margins in Rescue Prime, what sort of effect does that have on the performance? Quantifying.
So in the end, the only thing that reduces is the number of rounds, and it reduces by about 33%. And so it'll be 33% faster. Now, the relative difference in performance between Rescue and Poseidon depends in large part on the field you're working over. Rescue is very inefficient for large fields, but for small fields, it's very efficient. Of course, you need to take care to ensure that your field doesn't become too small, because at that point, Grosvenor bases are no longer the most performant attack, and you might be better off with a statistical cryptanalytic attack. In the research project that we just concluded, that the report was from, implementers observed that the optimized Rescue Prime was only 4 times slower than Poseidon over the same field, which is the nice 64-bit field.
I'm actually curious about smaller fields because we're considering using a 32-bit field. Do you think that would put us into the range where we have to look at different attacks? And were those attacks already analyzed, or would that be a new analysis?
You will be able to find a formula in the original Marvelous paper that introduced Rescue. That also includes smaller fields. I don't think we copied those formulas over to Rescue Prime or to that paper. My gut feeling says that where 64 bits gives you enough security against statistical attacks after 1 or 2 rounds, using only a 32-bit field will mean you need 4 or 5 rounds. That's my gut feeling, without having done any of the maths. I think you're still fine, but I would expect the statistical attacks to start dominating once your field is 16 bits or less.
I was also just curious about the degree of regularity that you mentioned and why the empirical data seems to diverge from this theoretical statement. Was the theoretical one just a bound?
I guess it is just a bound, but we do also observe that when we create random systems of polynomials with the same number of variables and the same degrees of polynomials, then we hit the bound exactly. So whatever is causing this discrepancy, it is an indicator that the polynomials we end up with are far from random. Now, it could be an indication that the polynomial model of the cipher that we have is actually redundant in some way, and that after we filter out those redundancies, then the description is optimal, and then we would be hitting the bound. It could also be an indication that there's just not that it's just not secure, or at least that this strategy of generating hash functions is just incapable of generating random-looking systems of equations, which is not necessarily the same as insecure, I should say.
I'm wondering about the concrete structure of, so I don't know much about hash functions in general. Hopefully some other people will also gain value from that. You have sort of some sponge, then some S boxes, and then this MDS matrix whose purpose it is to like increase diffusion. Is that roughly right? Could you like?
No, I'd say that's not roughly right. How about a share screen again? Hang on. I'll need to find the slides again. Give me a second, and I can clarify it perfectly. Share screen, share window, rescue prime, allow. Yeah, so in order to generate a sponge function, what you need is a permutation. And how you get that permutation, one way to get that permutation is to start from a block cipher and set the key to a predetermined value. Now, what the block cipher looks like, that's where you get the MDS matrix, and that's where you get the S box, and that's where you get the constants. Does that clarify?
Yeah, that makes sense. So the order is basically not the way I put it in.
Yeah.
But do you need the MDS matrix for diffusion? Is that right?
That's correct.
So that's not offered. So the sponge in and of itself doesn't provide sufficient amounts of that.
Correct. The sponge makes abstraction of the permutation. So it is actually literally assuming that the permutation is close enough to random.
Right. Okay. And so then it makes sense that you would need it. At first, it wasn't clear to me that the matrix was needed, but that makes sense.
I'm also curious, since Rescue uses x to the minus alpha as a S box.
It's not minus alpha, it's 1 over alpha.
Sorry, 1 over alpha. Is there something special about that? Or I understand you want it to be high degree, but is there something special about it beyond the fact that it's high degree?
Yes, it allows you to fold across rounds. So we essentially get 2n half rounds if you count the number of layers where there is an S box. But when you encode this in a Stark, your constraints are still only of degree alpha.
Right.
And you need only n number of iterations in the Stark to prove the correct evaluation of rescue. Or rescue prime, rather.
So that's, how does the kind of inverse order attack, because isn't one of the points here as well that you want kind of high degree in both directions? How does how, I don't know how it's defined, but like the attack that goes the other way, How does that work exactly?
So for hashing, I'm not sure there is an attack that goes the other way, but if you have an attack against the block cipher, then you demonstrate that the block cipher is definitely not random, and thereby you undermine the whole premise that went into the sponge construction. So we would consider that attack valid, even though we don't know how to turn it into a collision for the hash function that results. Now, the block cipher you can attack from either side, and just as there is a permutation, just as there is a polynomial that describes the output in terms of the input, there is also a polynomial that describes the input in terms of the output. And yeah, you want both polynomials to be of high degree, because otherwise you can interpolate based on a given set of input-output pairs. So if your polynomial is 20, then you can calculate that polynomial based off of 20 input-output pairs, and then you can predict the 21st ahead of time, which is not something that you should be able to do for a random permutation.
Okay, so it does have practical consequences, yeah, okay. I was curious about that.
Oh, I was also wondering, with respect to the some of the benchmarks, when you were looking at the design objectives, I think you said you mentioned it's motivated from the Stark paper. So, is there something in particular in the construct that, because I think it outperforms all the other hash functions in terms of air constraints, is that right?
Yes.
So yeah, was that specifically because you were working for, like, towards that design objective?
I guess it is an outgrowth of two things. One was, yes, that was our design objective, and the second thing is that we are essentially getting twice the number of rounds for free because of this folding technique where the alpha inverse S box allows us to describe our constraints non-deterministically in the Stark.
So, because Poseidon doesn't use that inverse S box.
Correct.
That's where you can get that increased performance for air constraints, is that right?
Yes, correct. Poseidon has the additional disadvantage that there is no high degree S box in the forward direction, and therefore they need many, many rounds to make the degree high.
Right, and they kind of so they use those partial S boxes to obtain that high degree, right?
Partial S box layers, right?
Yeah.
Yeah, correct.
So why is that sounds way less efficient? Why is Poseidon supposedly more efficient than Rescue then?
I think I disallowed my browser to share screen again. So the reason why Rescue and Rescue Prime is inefficient on CPUs is because you have to calculate x to the power 1 over alpha in, well, m times for every round. So that's a lot of big exponents that you're calculating. And the size of this exponent is roughly the same as the size of the field. And so for small fields, it's just a quick exponentiation that you barely notice, but for large fields, it starts dominating. Whereas for Poseidon, the degree of all the S boxes is constant, and that works a lot better for large fields because the cost is only quadratic in the size of the field, whereas for rescue it's cubic.
I don't know if what you sent, James, was related to this, but it would be very interesting then to see a performance comparison between those hashes over different field sizes, as Daniel was also, I guess, alluding to.
Yeah,
notwithstanding
link,
soundness,
some of the
of course.
later comments. I think that link I just shared is referring to the work you mentioned, Aaron.
Yeah.
Yeah,
on
the
our side,
updated comments at the end of it.
we spent a lot of effort optimizing Poseidon over this 64-bit field, and Maiden team has spent a lot of effort optimizing rescue. So I think we can somewhat confidently say that the gap is about 4x in favor of Poseidon. But that said, I think rescue has other advantages. It's cheaper in a circuit, and it seems to have a better security track record.
Have you tried reinforced concrete as well?
So the original reinforced concrete only works with a state width of 3, and so it can't really work with a small field like the one that we use. But the authors are going to publish a variant of it soon, specifically for this field.
And you haven't implemented that variant yet?
No, we haven't really spoken to them much, so I'm not quite sure what the variant looks like. But yeah, we'll be very interested. I'd be curious to hear your thoughts, but to me, it seems like maybe a good solution where we get good performance and resistance to algebraic attacks.
So I did spend some time trying to find weaknesses in hash functions that use lookup tables in the way reinforced concrete does, and I cannot find a reason why it would be just as attackable with Grosvenor bases as hash functions without lookup tables are. So, phrased differently, I think lookup tables are a robust way to thwart Grosvenor bases attacks. There's that. With respect to reinforced concrete, what makes me nervous is that the lookup table happens only in one round in the middle, and there are attacks that in a different context allow you to skip one round. Maybe those attacks only apply to the beginning or to the end, but I think it's conceivable that those attacks could be lifted to skip one round in the middle, and then I guess you don't want to have all your eggs in one basket or in one round in this case. But if a similar construction can apply a lookup table in every round, I would be much more confident to use that.
Mm-hmm.
So I want to ask one question. So it's actually related to Poseidon and rescue, because Poseidon doesn't use inversion route, but it uses the partial route. But recently there seems to be some discussion regarding whether or not partial route can make it easier to be attacked. And I forget the word. It's man in the middle, or probably it's just like brute force attack. What do you think about that?
I'm afraid I didn't catch most of the question.
Okay, let me speak that slowly. But the question is this: is that there seems to be some discussion regarding the use of partial route in the network, that this might actually bring weaknesses to against some of the attack. And now there seems to be a little bit more favor towards basically inversion, or actually we should just say x to the 1 divided by alpha or something like this. As long as it will increase the overhead on CPU, but it does kind of it doesn't bring a cost in inside the proof system. But it seems to have a lot of the security advantage. I know this is kind of very informal, but what do you think about that?
So the use of partial rounds has prompted attacks that attack precisely partial rounds. And that's the reason why the Poseidon team had to update their paper in order to stress not to use weak MDS matrices. Because if you happen to use one of the weak MDS matrices, then the attack applies and your hash function is as good as though it didn't have any partial rounds at all. So that's an interesting line of research. It shows that in order to make a hash function that uses partial rounds secure, you definitely need additional tests on your MDS matrix beyond the mere fact that whether this matrix is MDS or not. Yeah, I'm not sure I have anything else to say there.
In your the most recent paper where you'd optimized it, didn't you have some optimization of the MDS matrix as well, or was that just a given example?
So we did find well, I think Polygon Zero were the guys who pioneered the idea of using a circulant MDS matrix, and we found two more, and we are confident that using a circulant MDS matrix in combination with rescue or rescue prime is no problem at all, and that's precisely because every single round has a full layer of S boxes. With rescue prime, you need to run these additional tests to make sure that the candidate MDS matrix doesn't fall in a category of weak MDS matrices.
Do you mean rescue or Poseidon? Because I was thinking that maybe for rescue, you just need MDS matrices.
For rescue, you only need an MDS matrix. For Poseidon, you need an MDS matrix that has particular properties like the multiplicative order has to be high or different from one concrete number, something like that.
Got it.
Okay, do we have any other questions? No, okay. Well, I'd like to thank you, Alan, for your time, and that's been really helpful to explain rescue prime a little more. And,
Thank you.
Thank you very much.
Thank you, Alan.
Thanks.